If you have seen the previous lecture, previous video, you have seen that Fisher information matrix is very important. But now we want to talk about the details of that, how we derive them, why we put it in the loss, and all of the things that you need to know if you want to implement it in Python. So this lecture is just introduction to this important paper, just motivating you to read this important paper in 2021. So this is just the nuts and bolts of the previous lecture, previous paper. So continual learning is a much desired attribute for neural networks. For example, if we train a model to distinguish between images of a cat and a dog, and subsequently train it again to distinguish between images of chair and table, so this is task 2, and cat and dog is task 1, the model should be able to retain the information of knowledge of cat and dog as well. After learning chair and table, we don't want to forget the difference between cat and dog after training chair and table. So any degradation of the performance on the previous tasks after learning new ones is fittingly termed as catastrophic forgetting. Continual learning scenarios, if you read this beautiful paper, you will see that you can think about it like 3 different scenarios. It could be task incremental learning, it could be domain incremental learning, and it could be class incremental learning. So these are the possible configurations, but this point, for example, could be anywhere, as long as the loss is less than a threshold, the threshold. And so these are possible configurations. And what happens when you have 2 tasks, for example, A and B? This is for task A and this is for task B. So if you want to design it, you will focus on this region. This region is at the intersection of them. Or even if you have more than 2 tasks, just 4 tasks, for example, then this region is a good region because it is consistent with the fact that our loss should be less than a threshold that is acceptable. So we write the posterior, likelihood times prior and divided by your P of data. And if you take the log of that, as I showed you in the previous lecture, just take the log of the posterior, you will see log of P of theta. Because it's multiplication, it becomes sum, and this is denominator, so it becomes minus log of P. And so your task, when we say what is your loss with respect to parameters, it means that the log of your posterior, this one, it means that what is the log of your parameters given that you have all of the data. But as I said, your data is task A and task B, but they are independent. So until here, you can write that as log, because a B, it could be, you can write it B condition on A, theta condition on A, and B condition on A. But because A and B are independent, you can easily derive that this part, is just this part. But the problem is that this term is intractable. It's very hard to calculate. So let's see what we can do about it. You know that we can write Taylor expansion from high school. We used to do this like this. And we have higher order terms. But second order approximation for now is enough for us. Neglecting higher order terms, noting that derivative of loss with respect to theta is 0. Because it is 0, so only then at point and the Hessian remains. Hessian term remains. And this term is called Hessian because it's very important in optimization. Now you will see how it is important. So if you combine this 3 and 6, you will see that you can write that log of p theta conditional A like this. So we can conclude that p of theta condition A is just this term. And you say that this term, log of p theta conditional A, is just a term delta. And next we write this as -1 minus 1. It is still this one. But the reason that we write like that is because we know that we have a mean, the normal distribution. The Laplace approximation is just a normal distribution. That means this, and this is your variance. But variance has this interesting shape. And now you will see why Fisher information matrix comes. Because this is like I of A if you take the expectation. Because this is a probability distribution, but if you take the expectation of that, you will see we call it Fisher information matrix. And if you combine 7 and 4, you will see that this epsilon prime accounts for all constants. And this lambda is just a hyperparameter because it's a trade-off between learning B and not forgetting A. So I call it the parameter for catastrophic forgetting from A to B. And so this approach is a kind of regularization because you have weight regularizer and loss of B is separated from this weight regularizer. But the total loss is this. It's just you consider B, but you don't want to forget A. So this is the weight regularizer. You want theta to be as close as possible to theta A. And as I said, epsilon prime is just constant, all constant that you have. So we say a network has learned a task when its objective has reached the minimum in the loss surface. We know that the curvature of such surfaces represent the sensitivity of the network with respect to the optimum theta star. This sensitivity can be determined by looking at the direction along which theta changes. This implies the curvature is inversely proportional to a change in theta star. Hence, if the more the curvature, a delta increment can result in large increase in the loss. Curvature of a curve is denoted by its Hessian, and hence in our case, as the second derivative is of the log likelihood function of the posterior.